everyone. Thanks for coming back. How you doing? All right. We're going to continue thinking about inventing the future. And I have the great pleasure to introduce my colleagues to give you a quick picture about some of the incredible research that we're doing in that vein. So I'd like to introduce everyone all at once here. Professor Paulo Lozano is the Alemán Velasco Professor of Aeronautics and Astronautics, and also the director of our Space Propulsion Laboratory. Paulo is an expert in all things small engines, plasma physics, space propulsion, ion beam physics, and small sats and nanotechnology. So sit down and get ready for his talk. We're going to get ready for launch with Paulo's talk. He's also a winner of the Young Investigator Award back when, and a Future Mind Award. I want that award. That's awesome. So he really is thinking about inventing the future and the future propulsion to get us there. Professor Danielle Wood is an assistant professor of media arts and sciences, as well as AeroAstro. Danielle leads the Space-Enabled Research Group, seeks to advance justice on Earth's complex systems using designs that are inspired and enabled by space and our technologies. She's a scholar of societal development, has a background in satellite design, earth science applications, and systems engineering. As an alum from both the AeroAstro Department, Technology and Policy, then she went to work at the Aerospace Corporation, and I had the great pleasure to have her join me at NASA headquarters as well. Professor Richard Binzel is Professor of Planetary Sciences, Anna Margaret McVicker Faculty Fellow. That's our highest award for undergraduate education. Rick is one of the world's leading scientists in the study of asteroids and Pluto. Everyone knows about the New Horizons mission? Woohoo! And asteroids and OSIRIS-REx. You're going to hear a lot about that. He's really the world's expert in looking and categorizing the hazardous impacts associated with near-Earth objects. So if you want to be safe, please pay attention to Professor Binzel's talk. It's going to save all of us. He actually has an asteroid. It's number 2873 that bears his name. How cool is that? And finally, Professor Sarah Seeger. Sarah is our class of 1941 Professor of Planetary Sciences, Earth Atmospheric Planetary Sciences, as well as joined with the AeroAstro Department. Sarah is an astrophysicist and planetary scientist. Her research focuses on theory, computation, data analysis of exoplanets. How many are there, Sarah? 3,000 and counting, going to 4,000. We're going to hear, I think, all about TESS, as well as other missions. She does everything from CubeSats all the way to the Terrestrial Exoplanet Finder. She's also a MacArthur Genius Award winner, among many other. So just can't tell you how happy I am to be here with all of you to open up the afternoon. We're going to have a faculty panel, research inventing the future. We're going to have an incredible industry panel, and then we're going to have our students as well. The culmination is listening to our students and all of their research. So without further ado, we get started. And I think exploration, everything we do about exploration, just is to answer these three fundamental questions. Are we alone? Are there other habitable planets? And what about life? And when are we going to find it? Maybe within this decade? I sure hope so. We're on it. So from the far out to the solar system, and then here on Earth, I like to say that all of our exploration, all of our looking out into the universe is really about finding about us, about who we are here on Spaceship Earth. Heard this from this morning panels, but I'd like to share these with you in some incredible eyes on Earth. NASA's constellation of low Earth orbits looking down for any natural disaster, huge supercomputer simulations to look at drought and weather and sea temperature and sea rise and climate and clouds. I like to call this data the vital signs of Earth. We are at over 1 degree Celsius, 2 degrees Fahrenheit, global mean temperature from an average of 30 years from 1950 to 1980s, over 1 degree Celsius. That's concerning. The Earth is speaking to us. Are we listening? The Earth is screaming out to us about these vital signs. Carbon dioxide. We're constantly in different places, especially the Northern Hemisphere, over 410. We don't want to be above 400, over 410 CO2 parts per million. And what about our land ice? Greenland ice sheet, Antarctic ice sheet, that's 99% of the Earth's water trapped in ice. We're losing it at an astounding rate. Last year, over 400 gigatons per year. That's about 3 times the size of Texas. So from universe into our solar system, down to Earth. That's what you're going to hear about, some incredible research going on at MIT. Thanks for joining us. And we have Paulo's slides.
All right.
Is that right? Thank you.
Thank you so much, Deva, for the introduction and the invitation. Of course, I'm thrilled to talk to a lot of people that I already know. So this is fun, and a lot of people who actually were key in developing the technology that we have today for space exploration. Let me tell you a little bit about my personal dilemma. So if I can click this. There you go. So this is my personal dilemma. I am from Mexico. I grew up in my beautiful country. You can tell by my accent that I'm not from here. We didn't have a space program in Mexico. Actually, we have one now that is very recent and very incipient. But I grew up in the aftermath of Apollo and Voyager and all these great projects. And these great projects actually have something in common. They use very expensive, very large structures. So for example, I have in the screen, I have a communication satellite. And you can see how big this satellite is. So obviously, these are very expensive elements. We cannot have these things going on very frequently, like exploration for other planets, as we know, or either exploration of asteroids or other things in space. But these things are changing. Right now, we're changing from having very large, very costly space infrastructure to relatively small, actually the one that is on the screen is pretty small, spacecraft. And this is going to do something very important for people like me with this dilemma. Why is that? Because I couldn't have access to space science and space technology. I couldn't contribute to this kind of very interesting activity. But nowadays, people can actually do it. Because instead of having very infrequent projects, now we can have very frequent space developments with almost personal spacecraft. But just looking at the size of the comparison of these two very different systems, we can see that their capabilities are also going to be very, very different. So we cannot do everything that we already do with a big spacecraft on a very tiny spacecraft. But things are evolving in terms of technology in all aspects. So we can pack a lot of technology in very tiny spaces. But there are some things that actually we haven't been able to pack completely, and that's actually my passion. It's about propulsion. It's very difficult to actually have propulsion on one of these little satellites and make it move to very exciting and challenging places. So let me give you a point of comparison. This is a relatively big spacecraft. This is the Dawn spacecraft, which I don't want to steal Rick's thunder, but it went to visit two of the largest asteroids in the solar system, Vesta and Ceres. And the only way this mission was enabled was through the use of advanced plasma propulsion. So that thing that you see on below the black antenna, there is a white cover covering an ion engine. It's a highly efficient space propulsion thruster that works with a gas by ionizing it and accelerating particles electrostatically. Actually, if I just click here, you can see it working. That's how it will look in space. It's super cool. But it's also very efficient. In fact, the impulse that was created by this engine alone after it was launched into space was larger than the impulse that was required to put the spacecraft in orbit in the first place. So it's quite amazing. It enabled this kind of exploration. And again, uncovered many secrets and discoveries on these asteroids. I won't talk too much about this because I think, again, we'll talk about asteroids. But, there is one thing about this spacecraft. This very large engine, as our colleague in here is pointing to, cannot fit into a small spacecraft. So that's the key that we have been working on at MIT. I see some of my students are here, and between all of us, we have been able to create very small space propulsion systems that are as efficient as these very large ones. And this is an example. So obviously, there is a difference in scale. Amazingly, it's about the same thrust density, which is, that means that we can scale down these kind of propulsion systems, so now they can fit into these, very small spacecraft. I don't have enough time to actually go through all the different aspects that go into a very small technology like this. But what I can say is that in order for us to develop something like this, we need interdisciplinary work. As aerospace engineers, it's not possible to actually design something like this. We need to collaborate with physicists, we need to collaborate with material scientists, we need to collaborate with chemists and many other disciplines to actually be able to integrate something like this. Just very quickly, the way this works is very different from a plasma engine. In a plasma engine, you have a gas, you energize the gas with electrons, ionize it, and produce thrust that way. In this case, there is no gas. We have a liquid that wicks through some nanostructures that are inside this little device, and an electric field is applied that is very strong and actually evaporates ions directly from the liquid propellant that we use. And again, I don't have time to go through all the physics, which is the part that I love about this. But again, we can produce very efficiently thrust that can push little spacecraft around. And again, what this is going to enable in the future, and it's enabling already in low Earth orbit, but in the future, is going to enable these little spacecraft to do the ambitious things that we already do with bigger spacecraft like Dawn. Because we should be able to scale everything down. And now with the propulsion and with advanced communication systems and automation and all these advancements that are happening in parallel, we will be able to have fleets of these little spacecraft to go and visit a large number of exciting destinations in the solar system. That's something we cannot do today. Right now, Dawn is one in a 5-year to the decade kind of mission, and it's extremely capable. But it only goes to 1 or 2 places. If we had 100 of these devices, we can go to many different places. These are 2 near-Earth asteroids. One of them is Ryugu, the other one is Bennu. They look alike, so I don't remember which one is which. One was just visited by the Hayabusa spacecraft. The other one is visited by the OSIRIS-REx. But there are many more like this near the Earth orbit. You can see the blue lines in there are basically, it's an image by NASA, looking at the trajectories of all near-Earth or Earth-crossing asteroids. So it's plenty of places that we can go and explore. But in order for being effective, we have to do this very quickly. We have to go and visit hundreds of asteroids and establish their properties and learn from them, not only the science, but maybe practical things like mining and so on. So I think that there is a big future in actually exploring the solar system with small spacecraft. It's based on technology development, and a good part of that technology development is happening in places like MIT. So I'm thrilled to be here and actually contribute a little bit into this kind of endeavor, and maybe help a little bit in future generations avoid that dilemma of not being able to contribute to this fascinating activity. We should be able to do so by providing more access to people. Thank you.
Hello, everyone. It's such a pleasure to be here with all of you today. My name is Danielle Wood, and as Deva mentioned, I lead the Space-Enabled Research Group at the MIT Media Lab, but I'm also proud to call myself a member of the Department of Aeronautics and Astronautics. I'm here today to share our mission, which is to advance justice in Earth's complex systems using designs enabled by space. For us, this means 2 kinds of work. First, we would say a just world, just as Paulo has explained, is one in which no matter where you are born, you are free and able to use space technology to help advance development in your community. The second idea is we want to see all the ways that we can use technology from space to help reach the most important challenges of our society today. And one way to describe those challenges is with this list of the Sustainable Development Goals. They were curated by the United Nations, and in 2016, all the member nations of the United Nations, every country on Earth, has adopted these as our key goals between now and 2030. You see it covers a variety of topics, addressing basic human needs, addressing systems in our society, such as cities, and our systems of trade and consumption and production that are part of our global system of economics, but also our social systems. And of course, it addresses the planet, addressing issues of climate, making sure we are maintaining biodiversity on oceans and, of course, on land. So my goal is to ask, what are all the ways we could use technology from space to support the development leaders who are part of making these visions a reality? These development leaders come from many types of organizations. Some work in international agencies like the United Nations. We now have an MOU between our group here at MIT with the United Nations Development Program. Some of these leaders are in national governments. I'll soon be visiting some of the researchers and organizations in Ghana, looking at how their national government is using space. Some of these leaders are at the local scale, whether they're leading tribal governments in the United area and here in the Americas, or whether they're looking at city-level government decision-making. We also are very excited when we get to work with local entrepreneurs who know the detailed needs of a community. Our goal is to ask how we can redesign space systems, some that already exist, and some that we'll be developing along the way. We want to ensure we're using the best tools from satellite Earth observation, satellite communication and positioning, but also the knowledge we gain from human spaceflight and microgravity research, the activities we draw when we invent new technologies for space, but they inspire activities also on Earth. And we also believe that anytime a country advances their activities in fundamental scientific research, that's also a form of development, and it spurs new innovation. At Space Enabled, we bring together a team of people from a variety of disciplines. And in fact, we pursue our work with these development partners with 6 steps. We start by thinking from a design point of view, both engineering design, but also creative design, and we ask what problems are the development leaders seeking to solve. Next, we use a practice of art. So we're always reflecting on what does it mean to address development challenges from the point of view of understanding the human condition better through art. We draw heavily from social science. We read difficult texts in history, economics, anthropology. We use tools from social science to collect data and have a strong understanding of the social issues before we do any engineering design. We also bring together tools from engineering, especially building complex system models to help us understand how the environment and technology and humans are interacting. We often do innovation on systems related to satellites or observing the Earth, and often that leads to producing data streams. And those data streams can help these development leaders make better decisions in how they address the sustainable development goals. So I'll now give you 3 quick examples of projects within Space Enabled that highlight these activities. In the first example, I'm thankful for funding from a NASA grant from NASA's Applied Sciences program that is also focused on using NASA Earth science findings and NASA satellite data to focus on how we can address Sustainable Development Goal 15, focusing on biodiversity and life on land. Now, 15.8.1, under the Sustainable Development Goals, there are many details there, addresses issues of invasive plants. And here you see a satellite image that's in false color, but the red shows you vegetation, and the dark colors are showing water. Here we're helping a team, which is from a small company, which is an entrepreneurial company based in the country of Benin in West Africa. I've had a chance to visit there 3 times, and each time I go, I learn more about their innovation. Because there's an invasive plant called the water hyacinth that causes a lot of challenges in their local streams, lakes, and rivers. But they are harvesting the plant and converting it into a tool that absorbs oil-based pollution. Now, when I met this team, I was inspired by their innovation, and we asked whether they would like to use a space technology to improve their business. So now when I go to Benin, we're using data from satellites to track where the vegetation is moving. We're also using ground-based sensors that are based in the water and making ways to have low-cost sensors so this company can easily track what's going on in the water, but also from the air and from space. And the key question here becomes, what are the ways we can make technology like this easy and not frustrating? It may be available, but it's not yet in a format where it's easy for a team to use, who's also starting a company, addressing new customers, and looking at manufacturing issues in their day-to-day work. While we're in Benin, we're also collaborating with the national agency, looking at how they are using satellite-based data to map forest and to address the fragile mangrove ecosystems, which are so key to coastal health. The second example takes us on a microgravity flight. I want to highlight the work of Dr. Javier Stober research engineer here at Space Enabled. He's an expert in paraffin wax, your common candle wax. But it can be used as a possible fuel, hopefully for small satellites, and we're exploring its dynamics. What you see here is Christine Joseph, one of our graduate students, on a microgravity flight to ask the question, what happens when we rotate this wax in a liquid form? Does it give us the geometries we need to better be used and casted, we call it spin casting, into the right geometries for propulsion systems? What's exciting about this picture today is if you check out MIT News, you'll see this shot on a story not from Christine's engineering research, but from her policy research. So we combine these 2 points of view. She's both exercising and executing microgravity research. We're also studying what will happen in the future beyond the space station. And where will people all over the world send their research opportunities, especially from lower income countries, from those with less opportunity? Where can we do microgravity research in the next generation of the low Earth orbit ecosystem? So check out Christine's paper. You'll see the article there on MIT News. Finally, one more example takes us to our work in art. As we reflect on the anniversary of Apollo, one of my students, actually 2 of them, Liz and Rachel, they're reflecting, of course, on the amazing anniversary we just had of the Earthrise photo. And we are preparing an art installation, and we will be working first with the Intrepid Museum of Sea, Air, and Space. As part of this year's anniversary of the Apollo, we're going to create an experience where someone can sit on a bench and look at the Earth in the distance. It'll be a projection, but it's allowing them to experience what it might be like to be sitting on the moon and reflecting back on Earth as we continue to ask, what is our sustainable development path to both expand humans beyond Earth, but to care for our own planet? And this reminds me that as we continue to think about sustainable development on Earth, we also are imagining future societies beyond Earth. And we have an excellent opportunity now, before we make any long-term changes or decisions, to decide what will be the sustainable development for our future interplanetary species. Can we make now the sustainable development goals for the moon and Mars so we don't regret some of the choices we might make, and instead use our resources and create a society that's already going to be more accessible while continuing to care for our planet on Earth? So thank you.
Good afternoon. I'm Richard Binzel, professor of planetary science, and also I have a joint appointment in aerospace engineering. I'd like to welcome our special guests and our friends online. I'm a planetary scientist who studies asteroids and meteorites, and so it might not surprise you that I carry meteorites around in my pocket. And that's why I tried to come to a theme that's called touchstones for the future. You get it? So I'm going to talk about some of the legacies of Apollo and how that carries forward to the future. One of the legacies, as Maria Zuber touched on earlier, is the samples and the wealth of information from the samples. And one of the things that came from the Apollo samples was we began to understand and recognize that we have meteorites that come from the moon. Because we know the composition of the moon rocks, we can recognize material that gets splashed out of craters, impacts hit the moon, material gets splashed out, and some of that material arrives on Earth as meteorites. And so, Charlie, I like to think that these are following you back. They miss you, they're coming back to see you, so meteorites from the moon. And this is an anorthosite, one of your favorite kind of meteorites. And then moving forward, we also have meteorites from Mars. And the way we know that we have meteorites from Mars is because of the landers and rovers that have successfully gone to the surface of Mars, measured the composition of the rocks, measured the composition of the atmospheres. And when we look at these meteorites and measure the compositions and the trapped gases inside, it's absolutely a dead ringer that these things came from Mars. And so sort of side by side, the moon where we've been and where we're going to go back and stay, and then Mars, where we have our long-term goals. So there's 2 meteorites as touchstones for the future. Another legacy of Apollo is the cratering record on the moon, and the fact that we now understand that impacts are a natural process in the solar system, even today. And we knew that, or we're reminded of that with Tunguska in 1908, the comet Shoemaker-Levy impact into Jupiter back in the 1990s, and just a few years ago over Chelyabinsk, Russia, this large impact that occurred. And this was a spectacular bolide. It was in the middle of winter. And you see the bolide at the speed of light. The light reaches you instantly. So you go to the windows and look at it. And then 5 minutes later, the shock wave hits the windows. And there were thousands of people injured by broken glass because they were looking out the window and didn't think about the shock wave that might be following. And I guarantee you, I would have been one of the people looking out the window and not thinking about the shock wave. But what's the point? The point about Chelyabinsk and the Chelyabinsk meteorite is that it's really not a question of if we will ever be struck again. It's just really a question of when. And the good news is that large impacts are very infrequent. It's a very low probability that large impact will ruin our day. But the next large impact could be next year. It could be next century. We don't know. And that's the nature of a random threat. It's just a random process when these things come. And it turns out that we now have the capability of Earth-based satellite systems that can search for these asteroids and basically catalog what's out there. And in fact, Congress in 2005 issued a mandate that NASA should conduct a full-up survey of objects up to 140 meters in size, or 140 meters and larger, because these are the ones that will really ruin the day for an entire state or a country or small country. So this was a mandate, but it's yet to be done. And what's interesting is right now we have a system that is ready to build and ready to fly that can do the job. And there's an opportunity to launch this satellite system, the survey system, in 2024, and a cost savings of $100 million. And I wrote a little op-ed in Space News that just basically said, what are we waiting for? And as a planetary scientist, who I have no role in any of these survey missions, I'm just a planetary scientist who studies this problem, I believe that as we now have the capability to search for what's out there and simply know for sure whether there's any imminent threat or not, because we have the capability to do it, we have the moral obligation to do it. We have the obligation to protect our future. And the odds are completely in our favor that we can ignore this problem. But if we're wrong, I think it is a blunder of possibly tragic proportions. So my shtick, if you will, is we just ought to do the survey and find out. So, but a little more positively about what we find by just surveying what's out there is we will undoubtedly find objects that are rich in water. This is a type of meteorite, a carbonaceous chondrite meteorite that has about 5 to 10% native water in it. Astronauts are thirsty people, and so this would be a source for water for future space explorers. But also we'll find objects that are in low delta V, easily accessible orbits. And you can think about before we go to Mars, just like we didn't go to the moon with Apollo 7, we stayed closer to home with Apollo 7 before we went to the moon in later missions. And so before we might send astronauts to Mars, we might want to have a shorter mission in interplanetary space that goes somewhere and comes back. And these asteroids near the Earth, and Paula showed a wonderful diagram of that, if we find some that are really close and really in excellent orbits, we could have mission durations of 30 to 60 days, which would be about half the total time that we currently know about. So a survey would not only tell us about the security of our future, but it would also give us destinations for astronauts and destination for future space resources. So I think this is an important milestone for the future to find out what's out there. Thank you.
Good afternoon, everyone. It's a pleasure to be here. And as soon as my slide comes up, I'm going to start with an artist's conception of our neighborhood. It's on a logarithmic scale, so if you look at the bottom, every band is a factor of 10 away from the sun. You can see our terrestrial planets, the giant planets of our solar system, and spacecraft have visited every one of our solar system planets, including Pluto. And the Voyager spacecraft have just left our solar system. So if you look at this picture, beyond the Voyagers, we start to lose our solar system, we've passed it. The next objects, the next things out there are our very nearest stars. And this image is showing you a handful of sun-like stars that are close, relatively speaking. It's on a log scale, so while the Voyagers may be at 10 billion miles away, these stars are trillions and tens of trillions and further away. So we can't go there, we can't send spacecraft there. Indeed, the Voyagers would take tens of thousands of years to reach the nearest star if they were even going in the right direction. But we do want to, myself, it's my lifelong goal and the community of people working on exoplanets to find planets orbiting the nearest stars and to find planets that might be like Earth. So it turns out that probably every star has exoplanets. We already know of thousands of them. We know little more just that they exist in their orbits and maybe their size and mass. So we'd like to be able to study these planets and learn more about them, like whether they have oceans or maybe even signs of life in their atmosphere by way of gases that might be produced by life. So it turns out it's very challenging to study exoplanets and to find them. Our own Earth is 100 times smaller. It is 3,000 times less massive and 10 billion times fainter in reflected light than our sun. So if you were to set out to find planets, exoplanets, which method would you use? Size? That would be the easy thing. That's not really MIT style. Would you do mass or even reflected light? It turns out that finding planets by their size is the way that most of us are doing that right now. And here at MIT, we're Planet Finding Central. We are leading a NASA mission called TESS. We'll hear more about TESS this afternoon in one of our students' lightning student talks. In the bottom, though, you can see how transits work. The planets that are fortuitously aligned, they go in front of their star, as seen from the telescope, and the star drops in brightness by a tiny amount. Believe it or not, my job on TESS is to lead the team that finds planet candidates. It's actually a job, and we find so many planets, we almost have too many of them to keep up with, verifying whether these planet candidates are actually planets. But I'm going to use my time here, my few minutes, to tell you about another idea for finding transits. Indeed, there are many missions and many ideas. And this one involves a CubeSat that I conceived of right before I arrived at MIT a little over a decade ago. There's a picture of the class that worked on it for 3 semesters, and the student in the middle is holding like a model of it. Now, what we wanted to do was send up a fleet of tiny satellites. Each one of them would focus on one very nearby bright star and would be able to, in theory, or monitor the star for as long as possible, years. Although the stars do go behind the sun, so then they would have to hand off. But the thought is that the brightest sun-like stars, they're spread out all around the sky, and so we'd have a fleet of dozens of these things. And the goal was to build and launch a prototype. Now, the problem is that little satellites, especially little satellites, they get disturbed by their environment. Even the reaction wheels on them won't keep them stable enough to find planets by the transit method. And this actually is because the detector, the response varies quite a lot within a pixel and from pixel to pixel. So when I got to MIT and I wanted to do this project, I would tell people, let's say outside of MIT, we have to be able to precision point to 10 or 100 times better than anything done before in this mass category. And even some people wouldn't just say, no, no, you can't. They just laughed. They just would laugh that this is just crazy. At MIT, of course, great ideas are not crazy, they are doable. And we worked hard in the class and outside of the class with students in Draper Lab to develop the technology to precision point. And eventually the project moved to JPL. It got renamed and redesigned, and it doubled in mass and size. So it went just from, let's say, 5 kilograms to 10 kilograms. It's not too much. And JPL did a fantastic job. Many of the people in this picture, several people in the photo who were PhD students and technical mentors for the class, went on to work at JPL and basically built and operated the satellite. So it did launch in August 2017 on a SpaceX Falcon 9 rocket as cargo to the International Space Station, where here's a picture of it, that the astronauts took the picture as the CubeSat deployed from the International Space Station. And it's been operating on orbit now for about 1.5 years, actually. And we finished our science mission, and it's now being used as a test platform by people at JPL wanting to build other CubeSats. I only have one technical slide here, but I'm showing you the success in this mission. In pointing control, you can see this showing you pointing stability. It's on a log scale, and this is launch mass. So more massive things like Hubble at 10,000 kilograms, they point precisely because they have resistance to, more massive objects have resistance to having their movement changed. And you can see where Asteria lies. Let me get this here. And it's kind of hard to read this in a hurry. I only have a few minutes. But it is doing 10 to 100 times better pointing than anything in its mass category. And on your right side, you'll see a plot of flight data. And this is showing you in arc seconds. It's just a measure of spacing on the sky. And it's showing you in blue where the attitude control system points. It's kind of all over the place, but it's really still very good, even just with the attitude control system. And the red is when we turn on our precision pointing control. And it's actually a two-stage system where reaction wheels get us our attitude control to within several arc seconds. And there's an XY piezo stage attached to the focal plane, which moves very rapidly at about 10 hertz. As the stars start to drift away, the focal plane moves to keep the centroid of the stars on the same fraction of a pixel at all times. So it turns out that transits are only the first part of a long story. In exoplanets, when we want to find those planets around the very nearest sun-like stars, like the nearest 10 or the nearest 100 sun-like stars, transits won't work for us because they're very rare. The planets have to be aligned just so, and we won't be able to study atmospheres of Earth-sized planets transiting sun-sized stars. So our future in exoplanets is even more hard and more extreme than doing 100 times better than something that already exists. There's a concept called starshade. And starshade is a specially shaped screen that is tens of meters in diameter. And this screen would formation fly tens of thousands of kilometers from a telescope, both in space, both away from the tough effects of Earth's gravity. Starshade would block out the light of a star, one star at a time, searching for planets. In this illustration, there happened to be a Jupiter and an Earth there. And starshade has its own problems. It has to formation fly very precisely. It has to retarget and move across the sky for each one. And starshade was actually conceived of in the 1960s, and it's been revisited every decade. And there I am with a couple of my team members with one of the specially shaped petals. By the way, they're shaped this way because of diffraction. We can't put up a giant circular or square screen, or diffraction rings would kill the problem. And right now, starshade is there, being developed at JPL and Northrop Grumman Corporation. And it's our path for the future. Right now, it's still in its concept phase. It's not a funded mission yet. But various MIT students have worked on starshade, visiting JPL in the summers, and we have some PhD students doing orbit calculations right now. So that's all I have. I just wanted to leave you with this cover of National Geographic. It's this month, March 2019. So if you'd like to get the full story of what the frontiers are in exoplanets and how we're going to find those other Earths, please go in and get yourself a copy. Thank you.
Wonderful. Wow, it's great to hear those snippets of work. Maybe we can have the lights up because we do have time for a few questions. So if we can get the house lights up. I think you have your cards. Back to the Future, we're still 1950s style. Write a card, write a question on a card. I'll start off while we get a few questions. We have 5 minutes for questions in this session. And, but as we're collecting the questions, all right, you guys, you can answer either of these questions. Next breakthrough technology that we're working on, and or when are we going to find life?
Well, is that a question for us? Because I was going to ask.
Yeah, we'll go through the panel.
Well, I'll just be brief here because that's the most common question that we get asked. When are we going? We don't have a when for you. All we can say is we will have the capability to find signs of life in atmospheres of planets far away by way of gases that don't belong. And that's the James Webb Space Telescope. We're all eagerly awaiting for it to launch and operate. So that could be in a few years from now.
The next decade? Within this decade?
Within this decade, we'll be studying planets for that. For that, yeah.
Rick, what do you think?
Yeah, so I'll just follow on. I think it's an interesting question of what is life. And so I think we're going to find signatures that are really tantalizing. And to me, I think we want to kind of hold our applause, if you will, until we get that knockout case that this clearly is a sign of life and cannot be anything else.
You think first it's the chemical constituents?
I think, yeah, so we're already at the phase of studying the chemistry, where the chemistry for life is possible, but determining that that chemistry really is life, and there's all sorts of chemical imbalances and things like that that will, disequilibria that will help pinpoint that. But getting that definitive case, I think, is a tall challenge.
But if David were to re-ask her question, when will we get definitive case, that will be much further away.
We'll get the evidence. We have the evidence. The evidence is mounting, right?
Correct.
So in terms of technology, I think that we have to say something about software. It's extremely important to develop fully autonomous systems when the time comes to have these constellations of small satellites in an environment that it's very difficult to get to, one. And the other one is there is no chance for maintenance and communication with most of these spacecraft, even if they're small or large. Is going to be very complicated. So autonomy mixed with advancements in software, I think they are essential. And there is a lot of progress, of course, going on that, but we still need to develop the capabilities.
Yeah, fully autonomous.
Fully
I think
autonomous
lots of
missions.
times people don't realize how far Mars is, let alone outer solar system, let alone beyond. So fully autonomous systems is a big push.
I can also add on the software side. My team's imagining a future where we have software tools that help us understand the rich data we have about our planet, especially from satellite-based data. In the future, we're likely to have both commercially and government-operated imagers, but also other kinds of measurements. So our amount of data is only going to grow. And then I want this data to be useful to development leaders who are not specially trained to use it. So we're thinking about the kinds of tools that help us understand the data we have, which comes from airborne sensors, from space-based sensors. We want to answer questions of what's happening in the environment. We also want to ask what's happening to humans because of the environment, whether it's a storm coming or whether you're asking how humans are harming the environment. Then we want to ask what choices humans are making. And all that should feed into designing the next technology to get more data. So we want to make multi-part systems to understand this better.
It's a good, complex problem. Professor Binzel, when are we going to mine the asteroids? And what are we going to find useful? They wanted to know, yes, audience question, when?
When are we going to mine
When are we at
asteroids? I
those
get asked that question a lot. I have to find the right pocket. So I think I expect to see I'll say a test demonstration of in-space resource utilization. Probably not, maybe the 2030s. I doubt the 2020s, but maybe in the 2030s we'll see a test mission of in-space resource utilization, or ISRU. And I think the first thing that we are going to want or be able to access is water, because it's a pretty simple process of taking material that is water rich. We have solar power, you have heat to something that has water in it, you can boil off the water. So I think you can condense water. So I think water will be the first space resource. We'll see it demonstrated in the 2030s. Maybe by the end of the century, it becomes a commercially viable operation.
Thank you. Professor Seeger, finding exoplanets, what size aperture do we need? And do you think the coronagraph technology can compete with the sunshade?
The first question is what size aperture? For the very brightest stars in the sky, and for transiting planets, we use all photons we can that our detector will accept, all visible wavelengths. So the test mission, the cameras, their aperture is only 10 centimeters. They're wide field cameras, and they're looking, all four of them together are looking at a giant swath of the sky, 90 by 24 degrees. So in that case, it's tiny. If we want to use Starshade, or there's another version of Starshade, it's like, we call Starshade the external occulter. There's an internal occulter inside the telescope called coronagraph. And for those cases, blocking out Earth and trying to look at it in reflected light, we're getting so few photons. Even with a 2 or 4 meter telescope, it's like a photon per second or something, so little. In that case, we need a big aperture, the bigger the better. There are proposals for, people want to use the biggest aperture that you can squeeze into SLS, which they're thinking a segmented telescope folded up more than James Webb, maybe 16 meters in diameter. We honestly need bigger things. We need the students to figure out how to build telescopes in space or assemble them so we can have giant apertures. So for now, we're just looking at those nearest stars, the ones I showed on the artist conception, like 10 and 100, but eventually we want to look at 1,000. Now the coronagraph and Starshade, the best designs, and if we had as much money as we needed, we would use both of them in a complementary way. But the coronagraph inside the telescope requires the whole telescope to be incredibly stable, more stable than we barely know how to make that telescope as stable as possible, because any little vibrations ruin the wavefront and create little speckles that actually look like planets. So both coronagraph and Starshade are moving forward. In the best case, we would use both of them.
Thank you. We have a couple more great questions on propulsion, advanced launch capability, and the budgets and social impacts. But I'm sorry we're out of time, so we're going to take those questions to the break and make sure we're right on time for our industry panel. Thanks, everyone.
Thank you.
Thank you.